other things needs to be approximated. The typical approximation is applying this type of damping factors. And likewise, in this example of x directional inflow outflow, this is L1 has to be approximated. All the others can be determined. Well, that was running into a lot of trouble because the reason was, well, this is a long investigation that turned into this discovery. As it turned out, when you have a lot of those actions near the boundary, there are all these tangential velocity component, some reaction source terms there, all sorts of those things, and viscous effect as well. So we put all those original terms back into the system, and those are non-zero, so you cannot really neglect it. So if you try to apply this conventional Lodi into real, the hostile combustion system, those tangential and then viscous and reaction source terms are all there. But if you use the conventional Lodi treatment for wave amplitude, it's not easy to see from this expression, but you can cast that into so-called a temporal version, and there you see it clearly. The left-hand side is the temporal evolution of the pressure and velocity at the boundary. If it goes well, it will approach, without this term, it will approach zero. So you will approach that correct solution behavior. But if you have non-zero T, V, S terms, they are here. So your boundary value approaches to something else. What's the remedy? If you figure that out, it's actually very easy. Instead of using that, you'd use this type of, you'd have to put all this back such that your temporal boundary treatment becomes original damping term and with nothing else. So you know for sure if the P infinity is properly assigned, you will approach the correct asymptotic limit. So I used to like to call it like a Columbus's egg. It's so easy to figure that out once you know that, but it was so hard to find that out. It took a long time for the entire DNS community to figure that out. And so this, in fact, there was a little bit more story behind it. In fact, we had to use additional damping treatment for the tangential velocity term, and such that your final temporal version of the equation becomes like that. And finally, we have to determine those A coefficient there, which we chose to use a Mach number. And that ended this type of treatment. This shows the animation supposed to, right, sorry. This shows the vortex passing test. So you see that this is a conventional Lodi. You see those velocity field gets distorted, but the new formulation makes it really, really clean passing. And we have also done the ignition wave test. This is temperature spike in the middle, and temperature in radical species wave passing out to the all these open boundary. Oops, sorry. Well, let me go back. Let's show you. There's a little delay, but you can see that. You see all those the distortion of the wave in the new boundary treatment. It keeps it fairly round. It's still not perfect, as you can see, but it's still far better than the conventional treatment. So this was implemented into all these big simulations, and that allowed successful simulation of that. So that was one of my proud accomplishment in my early development of DNS. Okay, so let me switch gear. This is another example of how DNS can be actually used in the device level model simulation. So this is also related to the ignition problem that I covered in October, and we are using exact same DNS database to do this subgrid combustion model. In particular, the scalar dissipation rate modeling is really critical for combustion models, and that's what I'm going to talk about today. So basic intro one more time. This is the new idea of so-called low temperature combustion engines. This is a happy marriage between gasoline and diesel engine. The idea is you mix them up in advance and then ignite it by pure compression ignition. And that has a tremendous potential to improve efficiency, projected to be more than 20%. And that will be almost like a diesel engine efficiency for a gasoline engine. And it has, because you can burn lean, so you can reduce the NOx and soot emission. Everything looks great, except one of the challenges of these engines are, first of all, there is no ignition control, active control of ignition phasing. So it just set by auto ignition. So you really don't have a whole lot of control. So how to control ignition timing and over a wide range of operating conditions was really a challenge. And as a result, the engine speed map, the mean effective pressure and speed load map, the blue dots are conventional SI engine region. The equivalent HCCI engine region is operating range is compressed a lot. So there is the main research effort for the past 10-some years has been how to expand this operating region of HCCI engine. People have come up with a lot of ideas, although it needs to be refined to be practical. Some things like a spark-assisted compression ignition, and stratification introduction, and variable valve time, which is another effort to introduce mixture stratification by trapping exhaust gases. So all sorts of those fine-tuning has been developed. But from a fundamental point of view, we wanted to understand how this mixture ignites when there is some mixture fluctuation present. So this was a talk I gave last October, so I'm not going to elaborate any more on that. The reason I'm showing here is that I'm going to use exact same database to develop combustion submodel. So this was a CSP, computed singular perturbation application that was used to identify this fundamental characterization of ignition regimes. And so I'll just leave it at that. Today I'm going to talk about the RANs or LES submodels, which commonly is adopted in real engine simulations. So the idea, so the whole goal is that if this is a coarse grid RANs LES simulation, so we are hoping that this kind of box type of high fidelity simulation come from DNS can be filtered out to provide information about these RANs modeling. One of the key quantities that we are trying to model are these scalar dissipation rate for two. I'm going to elaborate on these mathematics in the next slide, so bear with me. All these tilde quantities are the average quantity. In the RANS context, it's Reynolds averaged. In the LES context, it's spatially filtered. And at the end of the day, your the cell averaged or RANS averaged mixture fraction, the concentration of the reactant species can be computed by the integral over the probability density function. Let me elaborate on that. This is a kind of busy figure, but basically the whole idea about this multi-scale simulation of realistic large-scale engines is that you want to treat the combustion in a reduced subspace. So that's the idea. Understanding that all this flame has a kind of one-dimensional structure, you can solve the CFD code without considering reaction. It's an inert transport equation, which is easier to handle. Then combustion is dealt in a reduced dimensional space. And that's the whole general idea behind flame net approach. So combustion is handled in a reduced dimensional space. Typically 1D, when you're using mixture fraction as a coordinate. We are trying to expand it to include some heat loss effect where total enthalpy is not conserved. So enthalpy variable H comes as yet another independent variable to describe the reactive space. So it is more complicated, but it still covers the one other important aspects of heat losses. So ZH is still reduced dimension compared to full 3D, so it still saves up time. So without dwelling onto a whole lot of detail in this figure, basically combustion code part is a reactive space. That's where all these reaction source terms are computed by this two-dimensional flame net equation. The transport equation, then you only need to solve for, in addition to momentum Navier-Stokes equation, you just need to add this couple more more transport equation.